Thank you very much for the in-person invitation, which unfortunately I could not honor. So now I'm alone in front of my screen. Thank you for giving me the opportunity to present these results, though. So the title looks a little bit complex, but I will try my best to guide you through it. Well, despite again I'm not physically in person. Yeah, just a few words of self-introduction. So my name is Alexia Auffeves. I'm research director at CNRS. CNRS is a French institution, but it has the very nice property of having international labs all over the world. And right now, I'm based in Singapore, and I'm co-directing a non-local team with my colleague Robert Whitney, who is based in Grenoble, France, and we dubbed ourselves the Quantum Energy Team. And we basically provide energetic analysis of all kinds of nice phenomena that you can find in quantum physics, like quantum measurement, quantum optics, quantum transport, and obviously quantum technologies. And in what I'm going to tell you about today, that will be mostly about energetics and thermodynamics of quantum optics, which has been one of the red lines in my research for a few years now, trying to bridge gaps between quantum optics and quantum thermodynamics. So when you try to do that business, there are actually two possible ways. Either you use quantum optics to probe results from quantum thermodynamics, or you use quantum thermodynamics to find some nice stuff in quantum optics. So for instance, in this paper here, which I will not tell you about today, we have used energetic witnesses to probe quantumness in fields that are propagating in waveguide. What I will mostly focus on today is the result of these three papers, starting in 2020 with Benjamin, who is in the audience, and then followed by an experiment with my colleague Pascal Senelard. And finally, this paper here, which will be the big chunk of my talk, which is revisiting optical block equations, giving them an energetic twist. So here is the menu. So for starters, I will start by saying a few words about how we go from quantum thermodynamics to something a little bit less known, but that in my group we like very much, that we call bipartite quantum energetics. And those who know me a little know that I attach a lot of importance distinguishing thermodynamics from energetics. Then that will be the biggest part, the application of the bipartite quantum energetics framework to optical block equations. Then I will say a few words about the experiment that was done in the group of Pascal Senelard that illustrates to some extent what we found in this paper before concluding and giving some outlooks of this work. So, well, usually when you talk about quantum thermodynamics, you start by showing a few good old faces from thermodynamics itself. So thermodynamics is captured by, well, say these two pictures here. One that gives you the first law. Thermodynamics is all about systems that interact with heat baths. Heat baths have some given temperature. So I will use a lot the beta here, which is the inverse temperature of the heat baths I will play with. So that's disorganized energy on the one hand, and on the other hand, you try to convert this disorganized and messy energy into some organized and useful energy that is dubbed work. So that's the first law. And there has been constraints that have been edicted by lots of big names in the field at the time. One of them being the fact that the entropy of isolated system can only increase. So this is called the second law of thermodynamics. And here I've written one of the most famous way of understanding the second law. If I pick this system S here, its entropy is always bigger or equal than beta Q, where Q is the heat it received from the bath. So this is known as Clausius law. And putting these first and second laws together, you find what is known as fundamental bounds that have a lot of interest when you try to build engines, for instance. And there is this citation from Carnot I discovered recently, I like a lot. Without the cold, the heat will be useless. So which really captures very well the results of this slide. Okay, so that's for the messages or the legacy of macroscopic thermodynamics. Now, when we go to quantum, so there are many ways of going to quantum, but the way chosen by the community, like more than a decade ago, is to focus on open quantum systems. That's the best or the favorite scenery of quantum thermodynamics. You do have open quantum systems that are coupled to thermal baths on the one hand, and that are classically driven on the other hand. So the kind of big questions that you encounter in quantum thermodynamics are typically if there are quantum advantages in quantum engine, can we violate Carnot bound and stuff like this. I don't know if Eric Lutz is in the room, but we discussed that 3 weeks ago and what I think about these violations. Then there is also the question of the work cost of maintaining entanglement or maintaining coherence against thermal noise. Can we define a quantum entropy production? What are the equivalent of fundamental bounds in the quantum realm? So these kind of fascinating questions that you can explore when you are in the field of quantum thermodynamics. And one of the most fundamental result that was obtained at the beginning, where the community started to build up, was a quantum version of the second law that was found out by Massimiliano Esposito and others, that can be written like this. So for any quantum open system S here, if it undergoes some entropy increase, while it is coupled to a thermal bath of inverse temperature beta, then we have this expression here, the increase of entropy of S, von Neumann entropy, plus beta times the increase of energy of the bath is always positive, because it always can be put under the form of some sort of relative entropy, okay? So this, I'm writing this because actually it will wear some sort of importance in the future of the talk. I will use this expression and modify it for other purposes. So that's for quantum thermodynamics, but now there is a question, if you want to explore all these very nice questions, one of the big practical questions is how do we really measure work and heat flows in quantum systems? Because work and heat, unlike internal energy or entropy, they are not state functions. Actually, they characterize processes. And typically in the classical realm, we measure work and heat by observing trajectories. So that's my contribution to the program, which is quantum trajectories. So here, actually, I tell you, in the classical realm, the way to extract work and heat exchanges, this is done by monitoring trajectories of the classical systems. And here is one beautiful result that was obtained in 2011, the measurement of Landauer's erasure bound that was done using the principle and the tools of stochastic thermodynamics. And so the problem is that in the quantum realm, this is not always possible. And most of the time, it's not possible to rely on these kind of trajectories because in the quantum realm, when you measure, you interact with your system and you can possibly input energy in the system. So you cannot rely on quantum measurement and quantum trajectories to find out what is work and what is heat, or at least not in a very safe way. So the ideal solution would be to be able to measure directly heat and work exchanges as energy changes in the bath and in the driving entities, meaning that ideally we would put in the same box the open system, which will not be open anymore because now there is also the battery and the bath inside the same closed and isolated system. So that looks very cool. But now the problem is that if everything is closed and evolves unitary, we need to define new thermodynamic concepts to extend actually work and heat in a framework where all the systems evolve in a unitary way. So we need for new thermodynamic concepts that are adapted to closed systems, in other words. And this brings me slowly to bipartite energetics, because the simplest scenery where you can study energy exchanges in a, say, well-controlled way is the bipartite system. So that's the scenario I'm going to play with now for some time. You do have two systems, A and B, whose dynamics is ruled by this time-independent Hamiltonian. And then we have conservation of the total energy of A and B and of the entropy because we are playing with unitary transformation. So conservation of the total energy and entropy of the bipartite system. Now, all along the talk, what I'm going to play with are what is dubbed thermal operation, where the coupling Hamiltonian V commutes with HA plus HB, which means that the change of energy of A is always exactly compensated by the change of energy of B, such that our local energy changes, we can really understand them physically as some energy exchange between A and B. So that's very simple. On the entropy side, you simply have this rule. The change of entropy of A plus the change of entropy of B corresponds to the change of mutual information between A and B. And so the local entropy changes, now they can be seen as the buildup of correlations between A and B, or entanglement in the case of a pure initial state. So now within this very simple scenery, the question that I'm asking is, can we characterize, or how can we characterize the nature of the energy exchanges between A and B? Can we define equivalent of work flows, of heat flows? What is the entropy production? And again, these are very new concepts to build in this new scenery that we have dubbed bipartite quantum energetics. So before going to the energetics, it's nice having a look at the dynamics. And in the dynamics, you can easily get that at any time we have a unique decomposition of the quantum state of A and B. There is the product state plus this term here that characterizes the correlations between the two systems. And if you put this state into Liouville equation, what you find, and tracing over A or B, you will find local dynamical equations. So for instance, here it is written for A. It's exactly the same for B. And there are two parts in this equation, one that corresponds to a Hamiltonian evolution, and that incorporates some effective Hamiltonian that is due to the action of the reduced state of B on A. So it can really be seen as a force that B exerts on A on the one hand. And what remains, the garbage here, it's actually the term acting on the dynamics that is due to the correlation. And it's not a CPTP map. It's really what remains in the Liouville equation once we have removed, say, the mean field evolution or what comes from unitary dynamics, effective unitary dynamics. So then it's nice to have the classical limit of this. So, and it's almost a definition of classicality here. If B is in the classical state, then it means that there are no correlations between A and B, which means that the correlation term here is 0, which means that A solely evolves under some effective Hamiltonian, which is HA here, and which corresponds to the fact that A is unitarily driven. So this is very absolutely consistent with the classical limit. Now going to the energetics. So from the little analysis before, what you see is that for each change of the joint state here, we can separate this into a change in the product states and a change in the correlation term. Now, if you search for the change of energy of A, then you easily find that it also corresponds to two terms here. One variation that is due to the change in the product state, and one variation that is due to the change in the correlation term. And now this term here, we have dubbed it bipartite work because this is induced by some effective Hamiltonian here. There is no entropy transfer, never. So it's very reminiscent of a workflow. So we have dubbed it bipartite work to be very careful because we are not in the usual framework of quantum thermodynamics here. And this is the work that is basically exerted by this effective Hamiltonian. And then the remaining term here, that's an energy flow that is like yielded by the correlation. It possibly comes with some entropy transfer. So we dubbed it bipartite here, heat or B heat flow. The nice thing with these definitions, beyond the fact that they are very intuitive in some sense, they also provide very symmetric definition of work and heat for A and B, which play no predefined role. And what you can see here, and this will have some importance in what will follow, correlations, they really play a central role in the way we define the energetic concepts. Don't have correlation, there is nothing to see, basically. Okay, so again, a little consistency check with the classical limits. If now B is in a classical state, then we saw that A evolution is unitary, and therefore A solely receives B work, which is totally consistent with textbook quantum thermodynamics. And one other nice property is that in the case of thermal operation, so where the total Hamiltonian commutes with the coupling term, then we can easily find these conservation laws here. So you see that actually the work of A on B exactly compensates the work of B on A, and same for the heat. And this can be, by a little hand agitation, be seen as a quantum translation of the action-reaction principle in this specific case of thermal operation. Okay, so now that actually I have all the conceptual tools I need, here is a list of the questions that I will address in the talk. So first of all, if I focus on bipartite quantum energetics, so which again addresses the case of a closed framework, then one question is, how can we distinguish experimentally the bipartite work and the bipartite heat? And what is entropy production, or a good entropy production, in this closed framework? And the other question that I will address is, how do the two frameworks compare? So we have a lot of pain to produce BQE, as we call it, bipartite quantum energetics. So at least, is it better? Does it bring more insights? What do we gain in introducing this framework? And to do this benchmarking between these two frameworks, what I'm going to need is a case that supports both description. And spoiler alert, this is going to be the optical block equations, because they can indeed be described both ways. So, so here is our case. So what we have dubbed closure of optical block equations, because usually block equations, they describe an open systems. And here we are going to treat them as a closed, as describing the dynamics of a closed system. So first of all, a little refreshment on the memory about what are the optical block equations. So they describe actually the dynamics of usually a two-level system that is classically driven, so historically by a laser. We dub the Rabi frequency omega. The frequency of the laser is omega L, and usually it's quasi-resonant with the frequency of the two-level atom. And on the other hand, this two-level atom is coupled to a heat bath of inverse temperature beta and typical number of thermal photons denoted N bar. So again, like I said, this is supposed to be an open system here. Usually it has been treated as an open system. So what textbooks provide us with is the reduced equation to describe the dynamics of the two-level system, which has a Hamiltonian part here that involves this driving term here, which is corresponds to the action of the laser, that I won't read because it's a bit boring, but you have it here. So it's a time-dependent Hamiltonian with the Rabi frequency here. So no Rabi frequency, no drive, in other words. And the other part here is the thermal dissipator that I have not rewritten, but it's a bona fide dissipator that involves the number of thermal photons here. Okay, and there have been a lot of debate in the past about what is work and what is heat in the case of optical Bloch equations. And so we have provided a consistent thermodynamics framework for this equation, where work appears to be provided by the drive, and it has this expression for the workflow. So I say provided by the drive because here you clearly see that it involves the time derivative of the driving Hamiltonian. Heat corresponds to the energy change of the bath that I will, as before, write that way. And the reason why we say we do have a consistent formulation of thermodynamical concepts is that it provides a positive entropy production flow, so which is captured by this expression, which again I have already mentioned before. That is reminiscent of the Clausius inequality. So this is all summarized in this paper, and Cyril can explain because Cyril is also in the room. That was very interesting to work with Massimiliano, who is the one who derived this kind of expression in the first place. Okay, but that's for the open system paradigm. So now the key is that the OBE, as we dub them, the optical Bloch equations, they can also be closed if they correspond to a dynamics that is taking place in a one-dimensional atom. So what is a one-dimensional atom? It is very simple. It's just an atom that interacts with field that can propagate just in one dimension. And this is typically what is described by circuit QED or waveguide QED. And this may be the hand of Ben here, I don't know, but actually this is what the kind of physics that you find in superconducting circuits. So in Benjamin group, in Cater group, and in many other groups playing with this kind of devices, and also in quantum photonics here, where here the emitter is a semiconducting quantum dots inside the directional cavity that is dubbed a micropillar, and we can typically describe the physics in the same way, with pulses that propagate in one direction of space. So here, just to scare you, is the expression of the Hamiltonian, but the take-home message here is that this is a good Hamiltonian, which is time-independent. Here you have the Hamiltonian of the atom, and here the Hamiltonian of the field that now, and the coupling term here that correspond to an infinity of modes, that are all the modes that are in the waveguide. And despite the complexity of this Hamiltonian, it is possible to solve the joint dynamics, unitary dynamics of the 1D field and the atom in some situations. And the fact is that for some initial states of the field that I'm going to flash you later on, the atom-reduced dynamic is exactly ruled by the optical Bloch equations. So for us, this is very good because now we do have the choice, either the open framework or the closed framework to describe what is the thermodynamics of the exchanges. So to solve the dynamics, in a closed manner, what has been introduced by the community a few years ago is what is known as the autonomous collision model. So the autonomous collision model, it means that you are going to describe the dynamics by sequence of collisions. And in the case of the one-dimensional atoms that we are interested in, we have the atom that is positioned here in x equals 0, and the field Hilbert space corresponds to time bins or units that are labeled by n, and that are captured by field operators Bn. So Bn dagger basically creates one photon in the unit n. And if you solve the dynamics of this system using the Hamiltonian I flashed before, what you can see is that between Tn and Tn plus 1, each unit k will move to the right and replace the unit k minus 1 in a complete conveyor belt picture. Okay? So now, if you look at the unit that is going to interact with the qubit, we call it the input unit, and we adapt the notation so that the input unit at time tn is Bn, and the output unit at time tn is Bn minus 1. Okay? So again, if you keep solving the dynamics, what you find is that the solution of the joint dynamics has this form here, where you see that the atom only interacts with the unit Bn between Tn and Tn plus 1. So it has this expression here, the quantum state of the field and the atom at time Tn plus 1 corresponds to this unitary evolution that impacts, that starts from the quantum state of the field and the atom at time Tn. Okay. And so the generator of this map here is this term Vn, which involves the spontaneous emission rate, delta T, which is the time that each unit needs to jump from one increment, and this term here, which is typical of a James-Cummings Hamiltonian, but now for one unit instead of one cavity. Okay? So, how do we recover the OBE from this collision model? The initial atom field state that we need to pick is the following. We say that at time T0, we have a product state between the atom and the field is each state in a product state that corresponds to, say, a product of displaced thermal field. So we have actually each cell, each unit that is filled by a thermal field of inverse temperature beta, and each unit is displaced, we are going to say, by the same quantity, alpha, which means, in other words, that if I pick the average value of the Bn operator at time T0, it will be alpha. Okay? And what I can tell you is that the OBE, they can emerge from this modeling. I'm going to flash very quickly how we do later on. And what is very nice here is that we are going to enter into the bipartite framework where the atom corresponds to one system and the field is the other, and the field plays both the role of the drive and the bath in the optical block equations. So how do we do? And these are the two most technical slides. We write down the change in the quantum state of the atom and the field between Tn and Tn plus 1. And we do a Dyson expansion at second order in Vn, which corresponds to first order in dt. This gives two terms, one term here and this term here, that we are going to trace either over S or over F to have the reduced dynamics of the field or of the atom, and then we divide by delta T. If we do that for the atom, the reduced atom dynamics that we get takes this very familiar shape here, where we recover here the Hamiltonian part of the optical block equations that is given by the first order in the Dyson expansion, and where we can observe, if you do the math, that the Rabi frequency is exactly given by the coherence of the input units, so it's set externally. And here, the second order here in the Dyson expansion gives us the thermal dissipator of inverse temperature beta. So all this is very nice, and this is known since a few years now by the community. So the OBE can be derived from a microscopic autonomous model. And if you do the thermodynamic analysis using these concepts, they are absolutely consistent with the open approach. Work is still provided by the drive and heat is still provided by the bath. So there is no change. In other words, we need to finish the business because we have not extracted everything we could from the fact that we have closed the optical block equations. The autonomous collision model, it can also support a closed approach in the complete spirit of the bipartite quantum energetics. And now, as I said, the two systems exchanging energy are the atom and the field. And the key skill to develop is the ability to track the correlations in the optical block equations. Hence the title of this paper that well, with the co-authors, we have dubbed it the 500-year paper. It took us some time to put everything together, but now it's on the archive. And if you have questions, you have both Samyak and Cyril in the room in principle. So how do we do this? We do the anatomy of a collision. This in the box is the former approach. We have the Dyson expansion here. And what we do is, in general, this term here, the first order, is directly injected in the second order equation. And then we trace over S or F. First order gives a drive, second order gives a dissipator. We have not followed this road. We have used another approach where we have actually split the first order term here in these three terms that correspond to, well, tensorial product between the field and the atom, and one term that captures the correlation. And these terms here, they also follow equations that can be written. And you see that now we have three first-order terms that we can send to extract the second-order variation. And if we do that, we have these three terms that, again, I'm not going to read here. What matters is that you get the big picture. And this is only at this point here where we realize that each second-order term now can be split into three terms that we trace over S and F to find our reduced evolution equations. So there is this scheme that kind of summarizes the approach for those who like pictures. So these are the first order processes that you can split into Hamiltonian and correlating processes. And they are the same in both approaches. But at the level of second order processes, what was just one term, if we would follow, say, the traditional road, becomes three terms, double drive, self-drive, or correlating processes in the closed approach or in the new approach that we have brought. So the dissipators now split into up to three terms. I say up to because depending on the model or the physics that we are studying, not all the terms will matter. And this is exactly what happens for the atom. So now if I go back to the case of the block equations, we had this open approach that was the standard route that would bring us here the thermal dissipator that was coming from the second order Dyson expansion. If now we apply our method where we track correlation, this guy here, we can show that it splits into two terms, one that has a Hamiltonian component and one term that quantifies the correlation. So, and we can write down at least this term here, which we have identified as a self-drive, which is a second order process that corresponds to the drive that is induced by the field itself generated by the atom. So you can imagine the errors that form a loop here. So that's, again, that's a self-drive of the atom. And this term, what is cool with it is that it can exist even if in the absence of external drive. This is something that you can see in spontaneous emission, for instance. And again, this term here that we even dare to write, this is what remains after filtering out the Hamiltonian processes. This is due to the correlation that remain. And again, this is not a CPTP map. We can play the same game with the field. And with the field, what we have, so at first order, we have nothing interesting because it's just the input-output equation. But at second order, so you have the flow of output photons minus the flow of input photons. It can be split into two terms as well here. One term here that corresponds to, that is given by the Hamiltonian processes. And if you do the math, you find that this term is exactly given by the change of amplitude of the field. So this term is accessible experimentally. using dyne experiment, either homodyne or heterodyne. The other term here is entirely due to correlating processes, and it exactly maps the change in the fluctuations of the field. So this is accessible using photo counting experiment. And what is very nice here, in our opinion, I mean, we really liked the fact that here these correlations that we track, they can be traced back in the field state change, even if they no longer exist, which is in particular the case with spontaneous emission, where at some point the atom and the field, they are completely disentangled, but you still find squeezing in the field, and this squeezing reveals that the atom and the field were once entangled. So this brings us to the energetics, but at this point, this is kind of very intuitive. So again, if we look at thermal operations here, which are actually thermal operation if the field is either in the vacuum or resonant with the qubit, and I will only focus on that because it's complicated enough. So we know that the exchange of energy of the atom compensates the change of energy of the field, and that the same thing happened also for the bipartite work and for the bipartite heat. So I will use only one notation for the work and one notation for the heat. What we can find is that the workflow is exactly given by the change of the field's coherent energy. So that's the modulus square of the amplitudes. Again, measurable in dyne experiments. While the heat, it's the change of the field in coherent energy, measurable in photo counting experiment. So the bottom line is that B work and B heat, they are measurable quantities here, and conceptually measurable. It's not a side effect. It's really definitions bring to these very intuitive expressions. So at this point, it is possible to compare the thermodynamical frameworks. And there is two parts, one for first law and one for second law. So here I remind you the sceneries of the open framework and of the closed framework. And in the open framework, what I told you is that the work is due to the action of the drive only. It only involves the time derivative of the driving light. The heat is the energy change of the bath, period. And the entropy production has this expression and is positive as it should. Now, if we go to the closed framework, now we have B work and B heat. And B work is due to the effective Hamiltonians, B heat to the correlations. Now, if you write this, you find this expression for the B work that involves now this effective Hamiltonian. And as we saw before, the effective Hamiltonian now has two parts. This part that comes from the external drive, but on top of this, there is the self-drive. And now if you put all this together, you find that actually the B work is equal to the regular work, the one that only involves the external drive, plus the self-work, that is the work performed by the self-drive. And if you inject the expression of the microscopic Hamiltonian, you find that this self-work, it scales like the atom coherence. So that's actually the key difference between the two frameworks. In the thermodynamic concepts, this is the self-work that makes the difference. On the heat side, the understanding is transparent in the sense that the heat in the standard framework, this is all the power that is emitted in the bath, but the B heat is just the incoherent power that comes from the fluctuations, and you must add this self-work flow that corresponds to spontaneously emitted coherent power. And this is allowed because there are many other modes than the driving modes, and the guy can emit because of the presence of coherence here. So here, for the sake of having one plot, you see the steady state self-work as a function of something that quantum opticians know as the saturation parameter here. quickly, because I guess I'm running out of time, or I don't exactly know, but the self-work, yes, my chairman, can you tell me how many minutes I have?
Time is out. I was trying to find out a way to tell you.
So how many minutes?
Yeah, the time is out. So if you can just is over. If you can just quickly conclude.
Okay, so the point is that the self-work here, always negative, which is consistent with the fact that the atom cannot provide work to itself, which means that the bipartite heat will always be lower by the heat than the heat. And now, if I jump on conclusions, if you now go to the entropy production, which is the benchmarking the frameworks using the second law of thermodynamics, you will find a tighter expression of the second law using bipartite quantum energetics, which comes from the fact that we have a greater knowledge on the field state that yields a lower entropy production. Too bad for the experiment, but that's a beautiful experiment. So I'm just flashing, and like Neo, you will know Jiu-Jitsu. Voila. Just a few words on the conclusion. So the questions that I addressed in the talk: can we distinguish experimentally B work and B heat? How do we define entropy production, and how do the two frameworks compare? So we have seen that B work and B heat, they are natural ways to characterize energy exchanges in a bipartite framework, and that they are measurable entities, especially if we look at regular Jaynes-Cummings Hamiltonian, but also if you look at two modes mixed on a beam splitter, you find also very nice expression of B work and B heat that involve displacement and squeezing. Now, the two frameworks, well, they are not equivalent. They differ by the presence of this self-work, which is a new concept that is experimentally measurable and that yields a tighter expression of the second law. And that's allowed by the capacity of our fantastic experimental colleagues to measure fields in 1D channels with high efficiency. And to conclude, I would like to say a word on open quantum systems, because the field has progressed a lot in the last years, especially because of these quantum collision models. And the first autonomous collision models, they have somehow purified open quantum systems. They have been able to derive master equation from closed system bath dynamics. And what we did is somehow upgraded the methodology, because we have unveiled correlations building up during single collisions, and we have studied their impact on the reduced dynamics. And that's a very general approach that we have used here for optical block equations, but I'm pretty sure it can be applied fruitfully to a very wide range of quantum open systems. And I thank you for your attention. Sorry for being too long.
Thank you very much. So we can take a few questions from the audience.
Hi, Alexia. Thanks for the interesting talk.
Hi, who is it?
Gonzalo Manzano.
Ah, hello.
So I have a question. So because in the framework you are proposing, so you insisted that you have a closed bipartite system, right, which is unitary evolving, so completely isolated. And of course, there the entropy production will be zero, right, in this dynamics, because it's just unitary and reversible. So my question is that, so of course to have
I don't agree with the premise, but ask your question.
My point is that of course to have some non-zero entropy production, you need to associate some degrees of freedom in which you cannot operate or that you cannot see, right? And I was wondering what are the degrees of freedom that you are assuming that you are not accessible in.
Yeah, so I was long enough actually, so I could not really elaborate on the entropy production, and I thank you for asking the question. Actually, here the entropy production it would come from the fact that we have a global evolution, but we look locally on systems. And that's the local versus global that is responsible for entropy production. So it's correlation erasure. That is one term that was already exhibited by Massimiliano almost 20 years ago. And but in the entropy production that Massimiliano had found, there was another term, which was the distance between the true state of the bath and the reference state. And in our approach, we have a tighter expression of the entropy production because the term that we use as a reference term for the bath is nearer the truth, say. Hope it answers your question.
But now it's working again, the microphone. So yeah, kind of. So yeah, because if you just neglect correlations, what you will get is essentially the change in entropy of the sum of the changes of local entropies, right? As entropy production. So then, yeah, I guess you are also kind of assuming that apart from that, there is something else that you cannot access. Now, in the case of Maximiliano, is that your kind of environment will thermalize, and then
yeah. Which is not the case for us because we make the assumption that the bath is accessible. It's the infinity of degrees of freedom that we treat in a unitary manner. I mean, that we describe, that the experimentalist can measure, etc. So we somehow bring both the dynamical and thermodynamical framework that is adapted to what experimentalists can now do. A bath is not a bath anymore. It's something in which we can find information as well.
Yeah, I changed the microphone. So yeah, so okay, I see. So so what is exactly the degrees of freedom that you can retrieve from the bath? So you said that you can still operate on the bath. You can retrieve some information from the bath. So it's not only the mutual information, let's say, between the two systems.
Yeah, I explained a little bit what I mean, the scenery here is, say, the one of circuit QED. So in circuit QED, you will have your field will contain both the drive and the bus that will be pulses that propagate, and what you will be able to do at the end of the interaction with the qubit is to perform some heterodyne or so homodyne measurement on your field in your waveguide. That's what is the bus.
Okay, thank you very much. Perhaps we can talk in another occasion. Like
With
more.
pleasure.
Thank you very much.
Thank you.
I had a very brief questions. I mean, I need to release everyone for lunch, but I was wondering if you looked at the self-work that you defined as a new concept I mean, we tried to do like some definition of like work and heat in open system, and that was some work with Adolfo Ali Resakani and Sahar Alipur, where we showed that actually work can be divided into like a part that is conventionally named as work, and another part that is necessary to stay on the trajectory, and other authors like call this the quantum work that comes from coherences. So it looks very like your self-work. So I was wondering if you looked into it, if it's the same term or any analogy.
Can you send me the reference you mentioned?
Yes, I will.
I would be in trouble to elaborate more. We built on a few papers already, so I guess I heard Halipur in what you said.
Yes.
Yeah.
I'll send you the references. And
yes, because there are a few papers. We don't agree with every choice that was made in these papers. Because I guess there was something with the coupling Hamiltonian that was not, in our case, we really have the total Hamiltonian that has three parts, HA, HB, and V, and we don't try to link V to any of the two other guys. So to keep the symmetry. And I think in these former papers that date back from 10 years or so, there was this kind of trying to integrate V in some of the systems. But that's all I can say. I'm happy to have your reference.
Yeah, I'll share it with you. Okay, so I think we should thanks Alexia again for this nice talk.
Thank you very much.